So what I'm hoping to do today in this talk is really to frame the conversation and the material that we're going to hear from the other leading voices in the interconnect space in the session this afternoon. And so what I'm going to talk about is some of the uses for optical interconnects in data centers and the drivers and application spaces to adopt some of these new technologies. And this is a relatively short presentation because I want to make sure that we give time to the other speakers and hear what they have to say. But in terms of an outline, I'll talk about some of the application spaces in terms of interconnects, how they're used today, and then how they would map in the future. Talk about reiterate some of the messages that you've heard from some of the speakers this morning in terms of what we're seeing in terms of growth drivers and some of the challenges which lead us to introduce some of these new optical technologies into application spaces where they've they're still emerging. And then talk about some of the targets and challenges going forward. And then hopefully that'll be a good setup for the panel discussion that we'll have at the end of today's session. Okay, so starting off, I wanted to just level set here and talk about how we use interconnects in the data centers today. And this is a very simplified cartoon diagram of where we see these different classes of interconnects. And so on the left-hand side here on my screen, I'm kind of showing you, this is like a cartoon drawing of a multi-chip package that we might see today. And so the interconnects of interest within this package might be things that are intra-chip, so shown by these gray arrows within a piece of CMOS. And then also chip-to-chip, so these yellow interfaces, which are various classes between like the big die and then these smaller chiplet die. And these chiplet die, for those of you who've seen some of the presentations this morning will recognize this. Some nice photographs were shown in those presentations, but those can be things like memories, HBM, and also SerDes for longer reach links to come off those packages. So then if you take one of these multi-chip packages, the way that these are typically packaged into a broader infrastructure is shown over here on the right-hand side. And what I'm really showing here again is a cartoon representation of a rack with multiple shelves within the rack. And so, and this is really borrowing from some of the ML infrastructure that we have at Meta, where we've got many of these multi-chip packages are typically meshed together by shelf level interconnects shown in red on a given shelf. And then those are then connected to a broader fabric through DAC cables, which are shown in black. So we have multiple shelves within the rack, which connected through DAC cables to a network switch. And then those network switches then scale out through optical links to connect to adjacent racks. And so this is really at a very high level how we build out very large infrastructures and build really what looks traditionally what would be considered like an HPC system, but in this particular case, as Bharath mentioned today, these are things that we use for things like our machine learning infrastructure. So that's kind of the status quo, and I wanted to kind of start with that to kind of have that picture in everybody's mind. So, Bharath showed this graph this morning as well, but I think it's worth reiterating it for maybe the people that couldn't attend this morning to kind of show this is kind of one of the problems that we're dealing with, which is if we look at the magnitude of how the models are scaling and the associated compute horsepower required to train these models, it's just becoming unsustainable. So on the left-hand side, this shows the evolution of some of these ML models as a function of time, and then the associated compute horsepower in terms of teraflops to train these models. And on the right-hand side is the resulting cluster power associated with that. And you can see, that this line gets up to really, unsustainable power levels very quickly if we just, continue the status quo growth curve and just project that forwards in an exponential fashion. And so this is, as I think a couple of the presenters this morning mentioned, and this scales very quickly to, many megawatts. And you can also see on the right-hand side the corresponding industry trend for some of the actual device accelerators. And I think, as was noted today, we're all trying to push off introducing things like liquid cooling as far as possible because of the cumbersomeness of trying to upgrade data centers with that kind of infrastructure. But you can see that very quickly by 2025 and 2027, you're getting to total power dissipations that will probably require that. So that's kind of a problem statement in terms of our evolving infrastructure. And I think the challenge for us as an optical community is that one way of solving this problem is to disaggregate what I showed you on the previous slide in terms of these multi-chip packages into separate devices in order to spread out the power densities. But we don't have a suitable high bandwidth, low power interconnect to facilitate that. So I think that's the challenge for us, as an industry and as an photonics community, to support these trends and try to kind of sustain the growth in the compute horsepower required as we move forward. Okay, so to talk about some of the challenging scaling challenges, first one I just mentioned was power. Now this is kind of threefold. First of all, power in terms of silicon power density. With the end of Dennard scaling, what that means is even though we can build more and more dense logic devices, the problem is the power density of those logic devices is also increasing. And so the power density means that, eventually we're going to have to, even though we can build larger pieces of silicon with more horsepower per silicon, we're going to have to split those silicon elements up just simply to deliver power to them and also to cool them. So that's kind of one of the first challenges that arises from this. And then also we have an infrastructure power limit in terms of how much power we can get from the utility and deliver to a given data center. So again, that bounds our ability in terms of power. Second challenge is related to that one, which is ASIC I/O density. So what this means is, on a given ASIC, we have to have increase, in order to scale the memory bandwidth and also the communication between different ASICs. We need increased data movement, but we have limitations in terms of packaging and in terms of chip feasibility, both the beachfront of those devices, which is typically where the I/O sits for reasons of routing and chip escape, and also just in terms of the bump pitches that can effectively, be developed. And so that's another problem, just escaping the die with sufficient bandwidth as we move forward. And then finally, related to that is signal integrity. So right now, the industry is wrapping our arms around 100 gig per lane technologies. And I think it's true to say that there's been enough investigation into 200 gig per lane, and this is 200 gigabits per lane. I realize we have a lot of computer scientists today who might think in terms of gigabytes, but 200 gigabits per lane looks feasible. It's certainly going to be challenging. The next IEEE project is certainly launched to start pursuing that right now. But there are challenges associated to even with scaling to that bandwidth per lane. Electrically, that's going to limit the reach that we can have both on PCBs and also over copper cables. And so we have to look at different system designs to address that. And then in terms of optical, we're kind of reaching the cusp, and I'm certainly looking forward to hearing a couple of presenters who I know are going to touch on this topic. Where does the transition between direct detect and coherent happen? 200 gig looks like maybe the cusp for certain reach applications. So I'm certainly looking forward to learning more about that. So then, looking at the different interconnects that I showed you on the first slide, the kind of what I've plotted here on this graph is efficiency as a function of reach for these different interconnect classes. And so the kind of the trend that you can see right here for the incumbent electrical interfaces, we do pretty well in terms of efficiency, but they tend to be clustered around the shorter reach limits. And as you kind of scale to longer reaches, and then you're forced to use more elaborate SerDes technologies, the power and the efficiency starts to degrade, and And certainly when you get over to optical, although you can support some pretty long reaches, you're paying a fairly high price in terms of the power that you need to burn to move the data those distances. And so I think the challenge, again, just to reiterate, is that we need some solutions which fit into what I've termed the disaggregation interconnect solution space. So low power interfaces, which are going to support these kind of reach requirements. And I'm going to map that out a little bit more in a table that's coming up in the next slide. Okay, so again, in terms of the target performance metrics that I think are going to be useful and some of the key performance indicators with these interconnects. So what I'm going to show on this slide is, first of all, the existing interfaces and the existing interfaces classes that we have today. And those are things that we're familiar with and we can realize, and then talk about what we might need to see in terms of future interfaces. So starting off kind of at the chip level, we have on-chip interfaces, which typically go very short distances. These are things which are contained inside of CMOS and have very high efficiencies associated with them. You can see over here, fractions of a picojoule per bit. As you scale these links and we go to technologies required to connect die together on a package, so MCM type technologies, the efficiency definitely takes a hit, and we start to move into the range of about half a picojoule per bit. And that's also true for on-package memory interfaces as well. But for all of these different classes of interfaces, we're able to sustain very high performance in terms of low latency and also a very low error rates, which is really required for memory-to-memory interconnects, which are very intimately tied to the compute capability that these devices have. And so kind of if you move to the next length scale and you introduce some of the longer reach interfaces, and this is things like compute buses such as PCIe, CXL, connections to system memory, DDR type interfaces, and then also networks or intra-rack, things like DAC cables and TwinX. The lane speeds definitely increase because you need to, minimize the number of wires involved, but also you start to see hits in terms of the, the end-to-end error rates, which then require that we might have to use forward error correction for these longer interfaces. And then also the total efficiency also drops as well. And so you start to get into the, multiple picojoule per bit type reaches. Moving further is where we start to see optics. So in reaches that go, in the hundreds of meters, tens to hundreds of meters and beyond, up to into the kilometer range, the efficiency degrades further. And so, right now we use these for our data center level interconnects, and the data center fabric are all optically based. But I think the challenge is, if you look at these optical technologies and then you map them back into things that you might like to bring close to the silicon, you've got a major, performance hit that we need to address. So I think the challenge that I'm going to lay out to the speakers that we have today, and what I'd like to do and come back to is it possible that we can define some new interface classes? So a shelf level interconnect, a rack level interconnect, and maybe a row level interconnect, where the reaches go from about sub-meter all the way up to 100 meters. And then can we achieve appropriate error rates, and can we achieve the low efficiencies? And I've left some of these question marks here. What do we think as a community we can fill in as some of these targets, and what should we be striving for, and what really is possible? So that's kind of what I would like to come back to in our panel discussion later on today. And also what kind of latencies can we achieve, acknowledging that, we can't really do much about physics and speed of light. So we're always going to be burdened with a time of flight latency, but what additional latencies are going to have to be included here for these kind of interconnects? Okay, so just kind of quickly summarizing here, I think, in my view, device and system disaggregation appears inevitable for the reasons of power that we talked about. And then some of the required bandwidths that we're trying to deliver, does that suggest that all paths lead to optical interconnects? And then finally, how do system architectures and device performance need to evolve so that we can enable these. And so again, we're going to try to come back and fill out that table. All right, thanks very much.
Thanks, Rob. Are there questions for Rob? In terms of your question about do all paths lead to optical, I presume you mean outside the chip. I suspect you're not really looking at within a chip.
Not yet. I was thinking more, chip-to-chip interconnects as we disaggregate the different IP blocks into separate pieces of silicon. Does that require, the bandwidths that require multiple terabit links between those chips? Does that mean that we are going to require optics in order to move things apart in an efficient fashion as we exceed what's possible from electrical interconnects?
Rob, this is Ram. I'm going to be talking a little bit about disaggregation. I just wanted to clarify the notions of device and system disaggregations. Are they like you're separating a monolithic chip into multiple chip? That's one form of disaggregation that people talk about, right? So if you can clarify device and system disaggregation just a little bit, that might be helpful.
Yeah, that's a great question. Maybe I can just share this, reshare my presentation really quickly and come back to that. Okay, so really what I'm talking about here, Ram, is if you look at this diagram right here, which is the way we currently do things today, both at the shelf level, if we were to just continue to scale the shelf level, given some of the power from some of these accelerators that I showed in the talk, right, exceeding a kilowatt, it becomes impractical to cool a shelf that's this dense today, right? And so at the shelf level, I think it's reasonable to expect that you're going to have to disaggregate this shelf and figure out how you replace these red PCB links with optical links in the future to connect these accelerators together. So that's one level of disaggregation. And then certainly, even within a rack, there's a limit to how much power I can deliver within a rack. So the racks may become sparser in terms of how many accelerators are possible per rack. Sure. And so again, you'd replace the DAC cables with an optical interconnect to enable the same kind of topology, but just more, at a lower density. So that's kind of the system level. And then if you actually look at the device itself, similar on the left-hand side right here, if you could replace these yellow links and then even inside the chip, these gray links with optics, to reduce the overall power and the power density of this overall package, that's also an angle that we could take as well, which would enable us to effectively deliver power to these devices and also cool them, but still connect them in an efficient fashion and get the same system performance that we would today.
Yeah, that helps a lot, Rob. I think there are several hierarchical levels where disaggregation concepts are being discussed. I think that all of them are valid and understand where you're coming from.
Absolutely, and I think one of the topics that was mentioned briefly today was in this morning's session was what level of I/O hierarchy do you need, and can you still build the same kind of hierarchy that you have today with these very efficient electrical interconnects? Or as we go to optics and we maybe add more forward error correction or more latency, do we need to reimagine, how we build systems, going forward to enable future scaling?